It's our pleasure to have Yuval Wigderson speaking today. He's a PhD student of Jacob Fox at Stanford, who and will graduate soon, I guess. And he'll be talking about some nice, I guess, algebraic combinatorics related thing entitled Covering the Hypercube with Geometry and Algebra.
Thanks, Andre, for the introduction, and thanks for the invitation. And thanks, everyone, for coming. I'm very excited to speak at the seminar. It's one of my favorite seminars throughout the pandemic. And so as Andre said, I'll be speaking about, it's a seminar on geometry and combinatorics. So I'm going to be talking about this question that is somewhere at the intersection of geometry and combinatorics and algebra. And everything I'll be talking about is joint work with Lisa Zauermann, she used to be a graduate student with me at Stanford, and now she's a postdoc at the IAS, and she'll be at MIT next year. And I put this quote on the first slide just because, I like this quote, but people have been thinking about hard problems related to cubes for, 2,000 years, and people have been reducing hard problems about cubes to other hard problems about cubes. And that's what I'll be talking about today. So just to give you an outline of what I'll be doing, so I'm going to start with just an introduction about some problems along the lines I'll be talking about constrained covers of the hypercube. And I want to give you some motivation about why these questions arise naturally in connection to various other fields of math. Then I'll move on to the main question I'll be discussing, which is this covering with multiplicity question. Then I'll tell you about our results, and then most of the second half of the talk will just be giving you a hopefully more or less complete proof of our main theorem, and then I'll wrap up with some other open questions. So let's get started. So the first question that you could ask is this question. What's the minimum number of hyperplanes that you need to cover all the vertices of the hypercube in n dimensions? And this is not a very interesting question because the answer is pretty clearly 2. You can do it with 2, so any 2 parallel hyperplanes will do it. And it's pretty clear that you can't do it with fewer than 2 because these points on the hypercube are affinely independent. Okay, so this is not a very interesting question, but there's a huge number of interesting variants of this question. And so before I talk about the ones that I'll actually be focusing most of the talk on, I want to give you a different type of interesting variant of this question, which is what's the minimum number of skew hyperplanes that you need to cover the vertices of the hypercube. So a skew hyperplane is a hyperplane where if I look at the normal vector, all of the coordinates are not equal to 0. Right, so in this example with the two hyperplanes were parallel to the axes, and the skew condition is saying that you're not parallel to any of the coordinate axes. Okay, so what's the minimum number of skew hyperplanes needed to cover the vertices of the hypercube? It's pretty easy to come up with a way of doing it with n hyperplanes. So here I've done it with 3 in 3 dimensions. So I can take these, in this case, 2 hyperplanes. This is the sum of the coordinates equals 1. This is the sum of the coordinates equals 2. By doing this, I cover every vertex except for these 2 vertices. And then there's a bunch of different skew hyperplanes I could take between these 2 vertices. So yeah, you can see that you can do it with n. And there's also a simple Folklore lower bound, which is on the order of square root of n. And the reason for that is just it follows from Sperner's theorem or the Erdős-Little-Wood-Offord theorem that any skew hyperplane can only cover a root n fraction of the points. So if anyone can only cover a root n fraction, you need at least root n of them to cover everything. And for, I think, 40 years, no one was able to improve either of these bounds, except just last month, Yehuda and Yehudayov were able to give, I think, the first improvement ever, where they improved this lower bound from n to the 0.5 to n to the 0.51, just some small improvement in the exponent. And this is not an easy paper. They use a bunch of different ideas to get this improvement. And as far as I know, these are the best known bounds in either direction. And so I believe this is an open problem. I won't talk any more about this, but I think it's a very interesting problem to improve either of these bounds. And as I mentioned, I want to point out that these these geometric questions, they're nice questions, but they also really have connections to other areas of math. So this question is known to have certain connections to certain circuit lower bounds. I won't really get into this, but this is why, say, Yehuda and Yehudayov were interested in this question, is because of these connections to TCS. Okay, so this is one interesting variant you could ask of this question about covering the hypercube. The question I'll be talking about for most of this talk is this variant of covering the hypercube minus a point. So,
Yuval, sorry, before you go further, can I ask one question about the previous slide?
Yeah.
So what if you require the normal vectors to be different? Does it make sense?
That's a good question.
So maybe this non-zero requirement is not even necessary.
That's a really good question. I haven't thought about that at all. But it's possible that would be interesting. Then I don't even know a nice upper bound, because this upper bound of n, you are using like n minus 1 parallel hyperplanes. Yeah,
well, if you allow zeros, I guess you'll be able to do something like n.
You can do it with n plus 1 probably.
Yeah, n plus 1.
Yeah, that's a good question. I don't know if I don't think, as far as I know, no one's thought about this question. So, but it's a good question. Yeah.
Okay, thanks.
Yeah, so the question I'll be speaking about for most of the talk is this question, which is, now I want to cover all the vertices of the hypercube except for one of them. So without loss of generality, it can be the all zeros vector. And I want to cover all the points while not covering this special point. Okay, so if you think about, so for instance, you can't now do these two parallel hyperplanes, because that way you will cover every point. And if you think about this a little bit, you'll pretty quickly come up with two different ways of doing this with n hyperplanes. So for instance, one thing you can try is that works is to take these n hyperplanes x1 equals to 1, x2 equals to 1, x3 equals to 1, and so on, that I've drawn here. And this is n hyperplanes, and it pretty clearly covers every vertex while not covering the special vertex 0. And there's another way of doing it with n, which is basically what we saw in the last slide, where I can take these parallel hyperplanes. So the sum of the coordinates equals 1, the sum of the coordinates equals 2, up through the sum of the coordinates equals n. And this will again cover everything while not covering the origin. And so if you think of both of these examples, and then you think harder and you can't do anything better, you could conjecture that n is the right answer. And that's true. So this is this famous theorem of Alon-Füredi from the early 90s, that indeed you do need at least n hyperplanes if you want to cover all the vertices of the hypercube while not covering the origin. And again, I want to say this is actually a question that arises naturally. So this question arose in work of Combgeo related to infinite Ramsey theory, so infinite extensions of Rado's theorem, which I won't really talk about. But yeah, this is a natural question that can arise in other contexts in math. And yeah, the theorem, again, is that you need at least n hyperplanes in order to cover all the vertices of the hypercube while not covering the origin. So I want to spend a little bit of time talking about this Alon-Füredi theorem. And the first thing I want to point out is that although this is a geometric statement about hyperplanes, every known proof of it is algebraic. And what do I mean by that? Alon-Füredi actually proved the following stronger theorem. So what they proved is they say, suppose you have any polynomial that vanishes at every point of the hypercube, but doesn't vanish at the origin. Then any such polynomial must have degree at least n. And as I said, this is a stronger statement. And the reason it's a stronger statement is that if I have any one of these hyperplane covers like this, I can multiply together all the defining equations of the hyperplanes. And this will give me a polynomial whose degree will be equal to the number of hyperplanes that I used. And it will have these properties that it vanishes at every point except for the origin while not vanishing at the origin. And so this is a stronger statement. The object considered in this second theorem is a more general object. And the magic that happens here is that this geometric question and this algebraic question happen to have the same answer. So they're proving a lower bound for the more general question, and that happens to match the upper bound for the specific question. And so that answers both questions. And I want to mention, I suspect many of you have seen the theorem, the proof or a proof of this theorem. You often see it when discussing Alon's combinatorial Nullstellensatz. So this theorem actually precedes the Nullstellensatz, but it's one of the things that motivated Alon to develop the combinatorial Nullstellensatz. And that theorem, this is really a special case of that theorem, and that theorem has a ton of applications in combinatorics. But I want to show you a proof of this Alon-Füredi theorem. And I'm not going to show you the proof through the Nullstellensatz, although it basically is equivalent to the proof I'm going to show you. And the reason I want to show you a proof is that in some sense, the same proof will be used for our main theorem later, except in sort of a more complicated way. So seeing this proof will be a nice build up to what we'll do later. So okay, so we're trying to prove again that if I have any polynomial that vanishes on all the vertices of the hypercube except for the origin while not vanishing at the origin, then its degree is at least n. And how do we prove this? So it's going to be a 3-step proof. Okay, so sorry, step 0 is, we can just, by rescaling, we can assume that the value at the origin is just 1. And now there are really 3 steps. So step 1 is we're going to convert this polynomial into what I call reduced form, which is just into a multilinear polynomial. So when I write out p, every time I have a term and I have any higher power of some variable xi, I just replace that by the variable xi. And the point is that when I do this, 2 things happen. First of all, the degree can only go down, right? Because all I'm doing is I'm replacing some higher powers by lower powers. So the degree can't go up. And additionally, this reduced polynomial agrees with the original polynomial on every vertex of the hypercube. And the reason for that is that 0 to the m is equal to 0, 1 to the m is equal to 1. So when I do this replacement of xi to the m by xi, I'm not changing the evaluation at any point on the hypercube. Okay, so step 1 was this converting to this reduced form. The second step is just a fact in basically the analysis of Boolean functions, if you like. But the fact is that any function from the hypercube to the real numbers has a unique representation as a reduced polynomial. So yeah, if you do Boolean functions, you'll think of this as the Fourier transform on the hypercube, but it's just a basic fact. So any function from the hypercube to the real numbers has a unique representation as a polynomial in this reduced form. And this you can prove just by linear algebra. It's just dimension counting. So the space of all functions has the same dimension as the space of all reduced polynomials, and that you can use to show this fact. So that's step 2. And now step 3 is, remember I have this function represented by the polynomial p, which is 0 at every vertex except 1 at the origin. And I can write down this polynomial, 1 minus x1 times 1 minus x2 times dot 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 times 1 minus xn. And this p tilde that I've written down is a reduced polynomial. And additionally, it agrees with the function p on every vertex of the hypercube, right? If I plug in the origin, I get 1. And if I plug in any other vertex, I get 0. So this reduced polynomial agrees with p. But we said that every function has a unique representation as a reduced polynomial. So this p tilde must actually be equal to the p bar I got by applying the reduction algorithm in step 1. And we said that the degree of p is at least the degree of the reduced polynomial. And we can see that this thing has degree n. And so that finishes the proof. So before I move on, are there any questions about this proof or about the theorem? Okay, great. So yeah, so that's the proof of the Alon-Füredi theorem. So now I want to talk a little bit about this this question of covering with multiplicity. And this was a question that was proposed by Clifton and Huang in a paper. It was published last year. It came out in the archive, I think, the previous year. And the question is the following. It's just a natural generalization of this Alon-Füredi question, which is what's the minimum number of hyperplanes that you need to cover every point of the hypercube at least k times? So now there's some parameter k. So I want to cover every point at least k times while not covering the origin. So just a higher multiplicity version of the question we just saw. So as a simple example, you can easily convince yourself that if k equals 2, then n plus 1 is the minimum. It's necessary and sufficient. So that it's sufficient, you can just do this picture. So here I've taken the hyperplanes x1 equals to 1, x2 equals to 1, x3 equals to 1, and so on. So that's n of them. That covers every point except for the origin. And actually, it covers every point at least twice except for the points of Hamming weight 1. And for those points, I can just take one additional hyperplane, which is sum of the coordinates equals to 1. And that does it with n plus 1 hyperplanes. And additionally, you can see that n plus 1 hyperplanes are necessary just because of the Alon-Füredi theorem. Because if I take any such configuration and I delete one hyperplane, I'll still be covering every point at least once. And by the Alon-Füredi theorem, I needed at least n hyperplanes for that. So if I add back the one I deleted, I need at least n plus 1. So this is a simple example. When k equals 2, this question is pretty easy. But Clifton and Huang studied this question in greater generality. And there's actually two interesting regimes of the parameters here, where you can either think of the dimension as fixed and the multiplicity as tending to infinity, or you can think of the multiplicity as fixed and the dimension as being large. In one of those two regimes, Clifton and Huang basically resolved everything. So one of their theorems is that if the dimension is fixed and the multiplicity tends to infinity, then this is the right answer. It's some specific thing with some little o1 term. And in fact, if k satisfies some appropriate divisibility conditions, such that this is an integer, then this is actually exactly the right answer without the little o1. And for all the other k, you can basically interpolate between such values. So they completely resolved the question for fixed dimension and unbounded multiplicity. And
Yuval, can I ask you a
yeah,
question?
Of course.
So here you assume that you can take the same hyperplane several times, right? Or
yes, that's right. That's right. Sorry, I guess, yeah, I'm taking a multi-set of hyperplanes, so I'm allowing to repeat as many times as I want. Yeah. Yeah, any other questions? Okay, so from now on, we'll be looking at the other regime where the dimension is large and the multiplicity is fixed. And this is also the regime that's sort of more natural if you're trying to generalize the Alon-Füredi stuff, because there that was the case of large dimension while multiplicity fixed at 1. So yeah, from now on, I'm going to think of k as fixed, and when needed, I'll assume that n is sufficiently large. Okay, so again, this is the question that they asked that we had on the last slide. And they came up with the following simple upper bound, which is the following. So we're going to construct such a covering as follows. So first, we start with the n hyperplanes, x1 equals to 1, x2 equals to 1, and so on. And if you think about these n hyperplanes, they'll cover, if a vector has t ones in it, then these guys will cover it exactly t times, right? Because these are exactly the things that count how many times you have a 1 in your binary representation. And so we've covered actually a lot of the vectors at least k times. The only vectors we have to worry about are those of Hamming weight less than k. And to fix those, we can just add these hyperplanes. So, the vectors with only one 1 in them, we've only covered one time. So we add sum of the coordinates equals to 1, k minus 1 times. And we add the hyperplane sum of coordinates equals to 2, k minus 2 times, and so on. And by doing this, we've fixed the problem and we've covered every point except for the origin at least k times while not covering the origin. And the number of hyperplanes that we used is n plus k minus 1 plus k minus 2 and so on, which is n plus k choose 2. So this is a simple upper bound, and Clifton and Huang thought about it for a while and couldn't come up with anything better. So they conjectured that this was the right answer, that for n sufficiently large, the n plus k choose 2 hyperplanes is also a lower bound, that this is really the right answer in large dimension. Okay, so this is their conjecture for the upper bound. What about lower bounds? So here's what they could prove on the lower bound side. So I already mentioned the case when k equals 1 and k equals 2, where there you can get these lower bounds of n and n plus 1, as I argued. And these match the upper bounds of n plus k choose 2. So for k equals 1 and k equals 2, this question is fully resolved. For k equals 3, the conjecture says n plus 3, and Clifton and Huang were actually able to prove a matching lower bound of n plus 3. But for all larger k, there's a gap between their conjectured upper bound, their upper bound, which they conjecture is tight, and the lower bound that they were able to prove. And the best lower bound they were able to prove was just n plus k plus 1. So there's actually a reasonably large gap where the lower bound they could get was just linear in k, whereas the upper bound is quadratic in k. And the main thing I want to say about these lower bounds is that just as with the Alon-Füredi theorem, although these are geometric statements, all the proofs that Clifton and Huang give for these lower bounds are algebraic. So in the same way as Alon-Füredi proved, a more general polynomial statement for the lower bound, Clifton and Huang were sort of implicitly studying this more general polynomial question. So the polynomial question is, what's the minimum degree of a polynomial that has zeros of multiplicity at least k on every point of the hypercube while not vanishing at the origin? And just as before, you can see that this is a more general notion. So any one of these hyperplane covers, where we cover every vertex at least k times while not covering the origin, if we multiply together the defining equations, we'll get one of these polynomials. And again, the number of hyperplanes we use is equal to the degree of the polynomial we get. And so this algebraic question, studies a more general notion. And to prove lower bounds on the hyperplane question, they were actually proving lower bounds for this algebraic question. Okay, so any questions about any of this so far?
So here the bound for k at least 4 follows in the same way from k equals 3k as you showed before, right? So you can just delete a bunch of like what k minus something hyperplanes and get a threefold covering.
Yeah, so that would only give n plus k, because for k equals 3, actually the bound is n plus 3. So they actually need to do, but what they do is exactly right. They actually really prove a bound of at least n plus 5 for 4, and then this reduction works for all larger k. That's right. Okay. So yeah, there's one more step to go from 3 to 4, and then afterwards it's just the same simple reduction. Yeah. Any other questions? Okay, so I want to talk a little bit more about this algebraic question of algebraically covering with multiplicity. So again, the question is, what's the minimum degree of a polynomial that vanishes to multiplicity at least k at every point of the hypercube while not vanishing at the origin? And just as a reminder, what it means to vanish in multiplicity at least k means that all the derivatives all the derivatives of order at most k minus 1 vanish at the point. So this is just, this is just the definition. So this algebraic question was actually studied even before Clifton and Huang. So it was studied by Ball and Sarah about 10 years ago. And what they were able to prove for lower bounds on this question was they proved that any such polynomial needs to have degree at least n plus k minus 1. And then, as I mentioned on the last slide, Clifton and Huang were able to improve this to get their lower bounds. So Clifton and Huang showed that when k is 3, you can get a lower bound of n plus 3 for this question. And when k is at least 4, you can get a lower bound of at least n plus k plus 1 for this question. So this is really how all of the lower bounds I showed on the previous slide come from. They're really lower bounds on this algebraic question. And all of these proofs, I won't get into it, but all of them use this theorem proved by Ball and Sarah, which they call the punctured combinatorial Nullstellensatz, which is just some sort of a natural higher multiplicity generalization of the combinatorial Nullstellensatz. So really, Ball and Sarah were interested in this question because they were really interested in proving higher multiplicity versions of the combinatorial Nullstellensatz and finding applications for that. Okay, so right, so the point is, everything I want to say on the slide is just that the way you prove these lower bounds is you really prove lower bounds for this algebraic question. And before I tell you about our results, I just want to mention that there's really a more general question that you could be asking. So the question I've been considering up to now is, what if I want to cover every vertex at least k times with a hyperplane while not covering the origin at all? But the more general question you could ask is, suppose I want to cover every vertex except for the origin at least k times while covering the origin exactly L times for some other parameter L. So, right, in the original Alon-Füredi question, these are equivalent because if I want to cover every vertex except for the origin at least once, and I want to cover the origin less than that, I only have one option, which is not covering it at all. But you could ask, what if I want to cover, every vertex except for the origin 15 times while covering the origin only 10 times or whatever? So yeah, for L equals 0, this is exactly the same question. And just as before, there's a simple upper bound you could come up with, which is of the form n plus k minus L choose 2 plus 2L. And the proof is just you take the k minus L fold cover that I showed you before, and then you add two L more hyperplanes, which is just L copies of a parallel pair. And so this is a natural upper bound you could come up with. And I just want to specialize it because these numbers will come up again on the next slide. The bounds this gives you for L equals k minus 3 and k minus 2 are n plus 2k minus 3. And for k minus 1, this gives you an upper bound of n plus 2k minus 2. And to go along with this geometric question, again, we have a natural algebraic question, which is, what's the minimum degree of a polynomial if I require that it vanish to multiplicity at least k on every vertex of the hypercube while vanishing to multiplicity exactly L at the origin? Okay, so yeah, I just wanted to put this slide in because I want to show you one of our results about this question. But yeah, I'll mostly be focusing on the original question. But are there any questions about this more general question that one could ask? Okay, so I now want to tell you about what Lisa and I were able to prove. And what we were able to prove is we were able to completely resolve all the algebraic questions that I've showed you up to now. So again, here I've written the two algebraic questions that I showed you before. The first one is, what's the minimum degree of a polynomial such that it vanishes to multiplicity at least k at every point of the hypercube while not vanishing at the origin? And then there's this more general question of, what if I insist on multiplicity at least k, but multiplicity exactly L at the origin? And we're able to completely resolve both these questions. So for the first question, we showed that for n sufficiently large, any such polynomial has degree at least n plus 2k minus 3. And we're also able to show a matching upper bound. So there exists a polynomial with these properties whose degree is actually at most n plus 2k minus 3, and therefore equal to n plus 2k minus 3. And for the second problem, we're also able to fully resolve it, where when L is at most k minus 2, the answer is n plus 2k minus 3 again. And when L is actually equal to k minus 1, the answer is 1 higher than that. And so there's something kind of interesting here, where for the algebraic question, insisting on some fixed multiplicity at the origin actually doesn't change the answer. The answer is just n plus 2k minus 3 no matter what, except when this multiplicity at the origin is k minus 1, and then the answer goes up by 1, turns out. Yeah, so these are our main results, are these exact answers to the algebraic questions. But of course, as I was explaining earlier, this implies lower bounds for the geometric questions. So again, here are the geometric questions that we've been considering, and our results immediately imply lower bounds for the geometric questions. So for the original question of Clifton and Huang, where we want to not cover the origin at all, our theorem implies that you have to use at least n plus 2k minus 3 hyperplanes. So this improves the previous lower bound of Clifton and Huang, which was like n plus k plus 1. And then also for this more general question, we also get lower bounds just from the theorem I showed you on the last slide, that when L is at most k minus 2, you need at least n plus 2k minus 3 hyperplanes. And when L is equal to k minus 1, you need at least one more hyperplane than that. And in particular, I showed you these upper bounds you get for this hyperplane question earlier. And so what these lower bounds match the upper bounds when L is at least k minus 3. So when the multiplicity at the origin is no more than 3 less than the multiplicity outside the origin, then we're able to completely resolve the hyperplane question. And in a certain sense, this is kind of why Clifton and Huang were only able to resolve the hyperplane question for k up to 3, but not any further. And it's basically because, well, I mean, we're proving more general results, but somehow when L is at least k minus 3, this algebraic technique really matches the upper bound you get from these simple constructions. And the final thing I want to say about these results, which I think is very interesting, is remember for this hyperplane question, Clifton and Huang conjectured that the right answer is n plus k choose 2 if I want to cover every vertex at least k times while not covering the origin at all. And I think the main upshot of our results is that, okay, this conjecture might be false, but if it's true, you aren't able to prove it with sort of purely algebraic techniques, where, I mean, purely algebraic isn't really well defined. But the point is that, for the natural for the natural polynomial generalization of this question, we're able to exactly resolve the question. And the answer is n plus 2k minus 3, which is smaller than this conjectured bound, this conjectured right answer of n plus k choose 2. So if you want to prove this conjecture, you can't only use these sort of purely algebraic techniques. You really need to do something that knows about the fact that you're really dealing with hyperplanes. And this is interesting because, as far as I know, for any question of this type, all lower bounds do rely on these purely algebraic techniques, like the combinatorial Nullstellensatz and things like this. And so somehow this is some sort of barrier result, where if you want to prove a conjecture of this form, you really need to go beyond these purely algebraic techniques, because for the algebraic question, the answer is actually, the correct answer is strictly smaller than the conjectured correct answer for the hyperplane question. So are there any questions about our results or anything else that I've said so far?
Hi, Yuval. Anurag here. So you could impose the condition on the polynomial that it's fully reducible, right? And that's basically the hyperplane question. But
that's right.
Would that be considered? And then maybe there's some algebraic way of seeing some lower bound. That's
right. Yeah.
Is that then purely algebraic or
geometric?
So
this is why I said purely algebraic in quotes.
Yeah.
And so really what I mean is that it can't be going through any technique that really works for all polynomials without any further assumption on the polynomials.
Yeah, sure.
And exactly as you said, I mean, the natural assumption you can impose on the polynomial is that it splits into linear factors. And then maybe you would be able to prove some lower bound for this question. I think the point is that somehow the combinatorial Nullstellensatz and results of that type don't seem to interface well with the sort of algebraic assumption being fully reducible or something like that. So yeah, I really think that what's going on here is that one needs to find ways of proving variants of the Nullstellensatz or strengthenings of it or something where some sort of assumption like complete reducibility is useful. And I don't know how to do that. Does that make sense?
Yeah, that makes sense. Yeah, thanks.
So in some sense, we can think of your result as this correct form of this punctured Nullstellensatz, or can you say that? Can you go that far?
Good question. No, so well, it's a little complicated. This punctured Nullstellensatz is more general. It applies to basically you have any grid over any field, and you can take any subgrid and impose some conditions on what's happening outside. Yeah, and so our techniques really don't seem to be able to do much beyond actually the hypercube and actually over the real numbers. I'll mention this near the end.
So not even 3 to the n over r.
I don't think so. I haven't thought about it a ton, but I really think that somehow our technique really wants to only work with just 0, 1 to the n.
Okay.
Yeah, so it's a correct form of this punctured Nullstellensatz, but only in this very special setting. And yeah, it'd be very interesting to find the appropriate common generalization. And I don't know exactly what that would be or how to prove it.
Okay.
No.
Okay, so adding on to that, maybe it's a silly thing, but what if you just have instead of 0, 1 to the n, you take a grid where all of these coordinate subsets, the 2-element subsets, they are different. Can you always reduce it to 0, 1 to the n? The problem?
Yeah, so I think that's the same because you can just apply an affine change of variables to reduce to this case. So I think that's just equivalent.
Yeah. If for ternary grids and higher, it's not equivalent, I think. But for binary, yeah.
So I think any binary grid is the same as the hypercube.
Yeah,
and then I don't think we know how to say anything about ternary grids, or even a bunch of 2-point sets and then a single 3-point set or anything like that. I don't think we can say anything about that sort of structure. Yeah, it's weird that somehow how limited this. Yeah. Okay. Any other questions about our results? Because I'm going to now start getting into the proofs.
Maybe a last quick stupid question about this conjecture. So if you try to do something like random, starting from this k-fold cover, and then you delete what your hyperplanes that you have at random, cannot you improve on this kind of trivial? Cannot you kind of squeeze some log out of this? Going from k-fold to I don't know, one-fold covering by deleting not k-1 hyperplane, but a little bit more, or it doesn't work?
Question. I don't think. Yeah, I don't know how to make that work. I mean, yeah, it's a good question. So one thing that's interesting is that Clifton and Huang, in their paper, they say that Noga alone pointed out to them a way of proving this conjecture if you already know that you contain the hyperplanes x1 equals to 1, x2 equals to 1, x3 equals to 1, and so on. So if your covering contains these n like coordinate hyperplanes, then actually this is the correct answer. And Noga had some nice Ramsey theoretic argument that showed that you needed at least k choose 2 more. And so somehow, I mean, okay, I don't know. It seems natural that you would want to use all of those hyperplanes. And so if you could prove that you do really need all of those, then you could prove this conjecture. And somehow that to me suggests, well, I don't know. It's different from the question you were asking, but I don't know how to do some random deletion and do anything better than just this trivial k-1 thing.
Okay. But it's an interesting thing that Alon
Yeah.
Okay. Thanks.
Yeah. Any other questions before I get to the proofs? Okay, great. So yeah, let's get to the proof sketch. And I'm only going to give you a sketch of this result, just our most basic result, where we have multiplicity at least k outside the origin and non-vanishing at the origin. The other results where you insist on multiplicity L at the origin can be proved. I mean, it's actually basically literally the same proof, but just for concreteness, I'll stick with this. And then I also claim that there's a matching upper bound, and we'll actually just see the proof of the matching upper bound. It'll come up naturally in the proof of the lower bound. So we'll really focus on proving this lower bound. And as I mentioned, somehow the proof is going to, in some sense, follow the same basic framework as the Alon-Füredi theorem. So recall that the Alon-Füredi theorem said that for k equals to 1, the degree is at least n. And the proof that I sketched earlier for this theorem had 3 steps. So the first step was converting p to a reduced form, where the properties you wanted the reduced form to have is that its degree is at most the degree of p, and it agrees with p on 0, 1 to the n. So as far as the problem is concerned, like p and p bar are sort of equivalent. That was step 1. Step 2 was proving that any function on the hypercube had a unique representation as such a reduced polynomial. And then step 3 was actually just you could write down an explicit reduced polynomial that agreed with p and had degree n, and that finished the proof. And so our proof sort of follows basically the same 3 steps, except every step is more complicated. And so I'm going to have now a number of slides where I'll show you for each step on the left what's going on with the Alon-Füredi theorem, and on the right what's going on with our setting, so we can see how this proof will work. So yeah, let's get into it. So step 1 is constructing this reduced form thing. And again, what was going on in the Alon-Füredi setting was if I have any polynomial and I replace any instance of xi squared or xi to higher power by xi, I don't change the evaluation of the polynomial on the hypercube. And okay, this is kind of obvious, but another way of saying this, the reason this happens is that this polynomial, xi squared minus xi, vanishes on the hypercube. So if I add it to my polynomial, I won't change the evaluation on the hypercube. And moreover, if I multiply this xi squared minus xi by any other polynomial q, and I subtract such a term from my p, I mean, this thing still vanishes on the hypercube. So if I subtract it from my p, I won't be changing the evaluation of p on the hypercube. And the point is that by just repeatedly subtracting objects of this form, I'm able to constantly reduce any higher power of xi that appears ever, right? Because I can pick, if I have any monomial that has some xi squared, I can take this q to be like the rest of the monomial. And if I subtract such a term, that's equivalent to just replacing that monomial by the same thing, but xi squared is now xi. So by repeatedly subtracting objects of this form, I can eliminate all the monomials that are divisible by some higher power of xi, that are divisible by xi squared. So that's what was going on in the Alon-Füredi theorem. So what do we want to do in our setting? Well, so we want to construct some reduced form such that, again, from the perspective of the problem, nothing has changed. So we want to convert p to some p bar so that the properties we care about are unchanged, so that p bar still vanishes to multiplicity at least k outside the origin while not vanishing at the origin. And so we can come up with the same sort of gadgets similar to what's going on here in order to do this reduction. So for instance, if I subtract anything of this form, so here I pick not necessarily distinct indices, I1 up through ik, and I subtract xi1 squared minus xi1 dot 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 times xik squared minus xik times any polynomial q. If I subtract something like that from my p, then I won't change either of these properties. And the reason is that this thing vanishes to multiplicity at least k everywhere on the hypercube. So if I subtract it from my p, then I won't be destroying either the property of vanishing to multiplicity at least k outside the origin, nor destroying the evaluation at the origin. So that's one gadget I can subtract. Another gadget you could come up with is this slightly more complicated thing. So here I'm only multiplying together k minus 1 terms, like what's up there, except now I also multiply by x1 minus 1 dot 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 xn minus 1 times any polynomial q. And again, you can convince yourself that this thing also vanishes to multiplicity at least k everywhere, and therefore if I subtract it from my polynomial p, I won't destroy either of these properties. Okay, so this is just something you can check that indeed these don't destroy the properties. And the point is that by repeatedly subtracting...
Sorry, Yuval.
Yeah.
I mean, does the second polynomial vanish everywhere or only on 0, 1 to the n minus 0? Sorry,
yes. It vanishes to multiplicity at least k outside the origin and vanishes to multiplicity k minus 1 at the origin, yes. But in particular, it won't destroy either of these properties. Yeah, thank you. I said, what I said was wrong, but yeah, thank you for that. And the point is that by repeatedly doing this operation, we're able to eliminate any monomials divisible by one of these two things, either divisible by a product of k squares or divisible by a product of k minus 1 squares times all the other variables, or all the variables. And I'm going to call such polynomials reduced. So I'm going to say that a polynomial is reduced if it has no monomial divisible by either of these two things. So I want to dwell on these reduced polynomials a little bit more. So again, the definition is that a polynomial is reduced if all of its monomials are not divisible by a product of k squares or a product of k minus 1 squares times all the variables. And you can pretty easily convince yourself, if you think about it for 5 minutes, that every reduced polynomial has degree at most n plus 2k minus 3. And this is basically just the pigeonhole principle. Any monomial whose degree is larger than this will contain either k squares or k minus 1 squares and all the variables. And so in the reduction lemma that I sketched on the previous slide, what you're able to do is by repeatedly subtracting objects of this form, you're able to get this reduction lemma that for any polynomial, there's a reduced polynomial whose degree is at most the degree of p, with the property that basically everything that the problem cares about is unchanged. So all derivatives of order at most k minus 1 of p and p bar agree outside the origin, and all derivatives of order at most k minus 2 agree on the origin. And this is the basic reduction lemma that, again, you can prove by just repeatedly subtracting these things I had on the previous slide. And one nice consequence of this is the second part of our theorem, which again was a matching upper bound. So this allows you to construct a polynomial that vanishes to multiplicity at least k outside the origin doesn't vanish at the origin, and has degree at most n plus 2k minus 3. And the way you can construct this thing is you pick your favorite polynomial of insanely high degree that has these properties. And it's very easy to, just use interpolation or whatever you like to construct a polynomial that vanishes to multiplicity at least k outside the origin, doesn't vanish at the origin, and will have some very, very high degree. But by simply applying this reduction lemma, you'll output a polynomial whose degree is at most n plus 2k minus 3 because it's reduced, and it will have the same properties. And so this is how you construct this matching upper bound, a polynomial that actually has degree at most n plus 2k minus 3.
Do you have an explicit construction or not really?
No.
Okay.
I'll get to this later, but it's really hard to write down explicit polynomials that do the thing you want. Algorithmically it's explicit because this algorithm is, the algorithm is very clear of just repeatedly subtracting these things.
But it takes a while,
yeah,
right?
It's exponential time because the number of monomials will be exponential, and you just need to scan through all the monomials. Yeah. So yeah, I guess it's not really explicit in that sense. Yeah. Yeah. Okay. So any other questions about these reduced polynomials? This was step 1 of the proof. Okay. So let's get to step 2. So remember, step 2 was about this thing that any function has a unique representation in reduced form. So in the Alon-Füredi setting, what this said was that every function from the hypercube has a unique representation as a polynomial in reduced form. And another way of saying the same thing is that if I give you the values I want a function to take at every point of the hypercube, so it has to be 5 here and negative 12 here and pi over here, if I give you those values, you can find a unique reduced polynomial that agrees with those values. And again, the proof of this is actually just linear algebra. So the point is that you can count just the dimensions of the space of reduced polynomials and the space of all functions like this, of the values on the hypercube. These two spaces have the same dimension. And this map from reduced polynomials to values is a surjective map. And that implies that it must be an isomorphism. And that implies this unique representation. This is just pretty simple linear algebra. And what we want in our setting is a slightly more general thing, because in the Alon-Füredi setting, we only cared about evaluation at points on the hypercube. But in our setting, we care about evaluation and also about derivatives. So the fact that's true in our setting is this, that if the information I give you is I want at every point of the hypercube, I tell you the values of all derivatives of order at most k minus 1, except for at the origin. And at the origin, I tell you the values of all derivatives of order at most k minus 2. So if I give you this long list of values, then you can find a unique reduced polynomial, reduced in the sense of the previous slide, that takes on these values and these derivatives. And the proof is literally word for word identical. It's just, you need to count the dimensions, but it's not too hard a numerative problem, that the number of such derivatives and values thereof is actually the same as the dimension of the space of reduced polynomials. So you count these dimensions, they're equal, and then again, this map is surjective, which implies that it's an isomorphism, and that implies that there's a unique reduced polynomial that takes the values that I prescribe for you. So again, I'm not going to do the actual counting for you, but believe me that it's not too bad. And this is the version of the step 2 that we need for our proof. So yeah, any questions about step 2? Okay.
Yeah, this somehow is not so intuitive, like if you would.
No, it's not. I mean, yeah, at some point when I was talking to Lisa, she told me that this was true, and I didn't really believe her. The fact that these two numbers end up being equal is, I think, not obvious. It's not too hard to do, but it's not obvious. And somehow, yeah, in the Alon-Füredi setting, it's pretty clear because you're just dealing with multilinear polynomials, and you just see an obvious bijection between that and like points of the hypercube. And here you're sort of counting different things, which is on the one hand, these derivatives, and on the other hand, these reduced polynomials in the sense of the previous slide, which is not having any monomials of this funny form. Yeah, I mean, it's true. And I don't feel like I have a really strong sense for why it has to be true.
But you don't have any like Fourier type explanation here either, or do you?
I don't think so. I don't
like
think
some nice thing that passes that doesn't do any counting kind of.
I don't.
Sorry,
Yeah.
if I add, this is similar to how in Grosvenor basis things happen, right? So you have like Grosvenor basis, and you have these standard monomials, and then there is a bijection like this exactly. And I think it does like this might just follow from that as well.
Interesting.
So it might be a part of the general thing in that way.
I see. So this.
Yeah.
Oh, that makes sense to me. I mean, I haven't checked, and it's been a while since I thought about Grosvenor bases, but that sounds plausible. Okay, so yeah, perhaps there is actually a real reason why this is true besides just counting. Yeah. Thanks for that, Anurag. Any other questions about step 2? Okay, so let's get to step 3. So step 3, I mean, I'm calling this slide just finishing the proof. So remember what we were doing in the Alon-Füredi setting. We wanted to show that any polynomial which vanishes on the hypercube but has value, say, 1 at the origin, has degree at least n. And what we did was we just wrote down this explicit polynomial. And we noticed that it's reduced and it agrees with this function p on the hypercube. And then just because this thing has degree n, steps 1 and 2 immediately imply that we're done. They immediately imply the Alon-Füredi theorem. So what's the analog in our setting? So again, we're trying to prove that any polynomial which vanishes to multiplicity at least k outside the origin, while not vanishing at the origin, has degree at least n plus 2k minus 3. And basically, by steps 1 and 2, it suffices to prove this just for reduced polynomials. And this is actually very hard. So this is the hardest part of the proof. And the reason it's hard is that in the Alon-Füredi setting, there was exactly one polynomial. There's exactly one reduced polynomial that had the relevant property, and it was this one. I mean, there's a one-dimensional space of them, so they're all scalar multiples of this one. But in our setting, there are very, very many reduced polynomials that vanish to multiplicity at least k outside the origin while not vanishing at the origin. So somehow in the Alon-Füredi setting, this was pretty easy because we just write down basically the unique example that does this and check that it has degree n. But in our setting, there's very many examples, and there's a high dimensional space of examples, and we need to check that all of them have the appropriate degree, n plus 2k minus 3. And so, so the rest of the proof will just be about how we prove this fact. So again, what are we trying to prove? Just for notational simplicity, I'm going to let Vk be the vector space of reduced polynomials that vanish to multiplicity at least k outside the origin. That vanish to multiplicity at least k outside the origin. And remember that every reduced polynomial has degree at most n plus 2k minus 3. And we want to prove that actually a matching lower bound. So to finish the proof, it suffices to prove this lemma, which is that for every non-zero polynomial in the space Vk, its degree is actually equal to n plus 2k minus 3. So this is what we have to prove. In order to do this, let's let this function hk be the linear map, which just sends a polynomial to its homogeneous part of degree n plus 2k minus 3. So just throw away all the monomials of degree less than n plus 2k minus 3. Only keep the ones of degree equal to n plus 2k minus 3. And then this lemma is equivalent to the statement that this function hk is injective, right? That if I take any non-zero polynomial, then its value under this function hk will not be 0, which implies that this polynomial has a term of degree n plus 2k minus 3. And now we'll use some magic linear algebra fact, which is why I called the slide linear algebra to the rescue. So to prove that hk is injective, that's equivalent to proving that the dimension of the image of hk is equal to the dimension of the domain, right? Because the linear map, if it's injective, I mean, being injective is the same as preserving the dimension on the image. And in fact, this is equivalent to proving a lower bound, that the dimension of the image is at least the dimension of the domain, because the other inequality is trivial. And so in order to prove this lemma, it suffices to identify some subspace wk whose dimension is equal to the dimension of vk, and such that this function hk is surjective onto the space wk. And this is one of these like magic linear algebra facts that I feel like I never appreciated when I was first learning linear algebra. We're trying to prove that a function is injective. I don't know how to prove that this function is injective directly, but it suffices to prove that it's surjective onto a space of the correct dimension. So we're trying to prove injectivity, and it suffices to prove a totally different notion, which is surjectivity, and plus some dimension counting. And yeah, I think this is one of these amazing magic linear algebra facts that you can convert one problem into a totally different problem, and this actually allows you to solve it. So yeah, I don't know how to prove that this map is injective, like directly by analyzing it. I only know how to prove that it's surjective onto a space of the correct dimension. Okay, so any questions so far? Okay, so to wrap up, it suffices, this is just what I had on the previous slide, it suffices to identify the space wk with the correct dimension such that this function is surjective onto this subspace wk. Okay, so how do you find this thing? Well, if you work out some small examples, you can guess that the image should be this rather non-intuitive space. So we're going to let wk be the space of all polynomials which are spanned by things of this type. So things of this type are the product of all the variables times the product of a sum of some specific power of all the variables. Sorry, yeah, a sum of like the mth power of all the variables times just a bunch of even powers of the variables where this has the appropriate degree, so that this thing has degree 2k minus 3. And again, I mean, I don't know how you would come up with this except by just doing some small examples, and this turns out to be the right thing to pick. So I claim that this is really the image of this map, HK, so it suffices, I claim that this is the WK that we were looking for. So we need to check that the dimension of this thing equals the dimension of the domain, and that HK is surjective onto it. Okay, so here's a fact, and this is just counting, but you can count the dimension of vk, the space of reduced polynomials that vanish outside the origin, to multiplicity at least k, and you can count the dimension of wk, and they turn out to be equal. They're equal to this specific binomial coefficient, although we won't need that. The point is just you can count them, and they have the same dimension. And again, I don't have a particularly good reason for, I mean, okay, the reason they have the same dimension is because this really is the image of this map. And you can guess this is the image by doing small examples. I don't have some good a priori reason why they have to have the same dimension, but they do, and it's just something you can check. So it suffices to prove that this function hk is surjective onto the space wk. And to prove surjectivity, it suffices to prove that we can hit all of these basis elements that span the space wk. And you can check, it's pretty easy to show surjectivity onto a basis element where one of these exponents di is positive. And that just follows by induction on k. So these wk's have some nicely nested structure. Basically, there's a bunch of basis elements where one of these di's is positive, or at least one of the di's is positive, which are really coming from a lower dimensional setting. So surjectivity onto those is pretty straightforward, just by induction on k. So all that remains is to deal with the one remaining basis element where all of these di's are 0. And so the key lemma is this, that we get surjectivity onto this basis element, where, so x1 up to xn times the sum of the 2k minus 3 power of all the variables. And so we need to prove surjectivity onto this. So it suffices to prove this lemma that there's some polynomial in the space vk, such that hk of r is in the space wk, and the coefficient of this basis element in hk of r is non-zero. Right? Once we get that the coefficient is non-zero, then because we already got surjectivity onto all the other basis elements, we can get surjectivity onto this basis element as well. So does everyone believe that it suffices to prove this key lemma? And we're already making progress, right? Because before we were trying to prove a for all statement that for every polynomial in Vk, its degree is n plus 2k minus 3. And we seem to be in better shape because now it suffices to prove a there exists statement. It suffices to prove just that there exists some specific polynomial r with all these properties. So, okay, how do we prove this? Going back to what Andre asked before, I don't know how to write down an explicit such r. It seems very hard. So instead, we apply the only thing that we know how to do, which is to start with a high degree polynomial, and we apply the reduction algorithm to it. So this polynomial vanishes to multiplicity at least k outside the origin. So if I apply the reduction algorithm to it, I'll get an element of Vk, which remember Vk was the space of reduced polynomials that vanish to multiplicity at least k outside the origin. So I apply the reduction algorithm, I get some polynomial, and then the hope is that this polynomial that I get will be the magic r that I'm supposed to get to prove this key lemma. So we need to check that this polynomial r, the coefficient of this basis element, when I look at the homogeneous part, is non-zero. So you do a bunch of computations using a bit of the theory of symmetric polynomials and just a bit of elbow grease to actually do the computations. And you find that when you start with this polynomial, you apply the reduction algorithm, then you apply this function hk, and you compute this corresponding basis element, this corresponding coefficient. That coefficient is equal to this complicated sum. So the thing that we would like to be non-zero is this complicated sum. So I sum over all sequences of positive integers that add up to k minus 1, and I take a complicated alternating sum of a bunch of binomial coefficients. This isn't a typo. They're not quite the same. So the second one through the tth one are all k minus 1 minus the corresponding element, choose that element. But in the first one, we actually get choose that element minus 1. I mean, turns out, again, this is just what you get from doing the computation. Okay, so to conclude, it suffices to prove this lemma, that this complicated sum is non-zero. Okay, so any questions about anything so far? Does everyone believe me that it suffices to just prove this lemma, that this very complicated sum is non-zero? Okay, does anyone have any ideas for how you could prove that something like this is non-zero? Yeah, so I mean, this is, it's really not obvious. This past quarter, I was attending a class taught by Jun He, and at some point in the class, he said this quote that I found very deep, actually. He was talking about proving the hard Lefschetz theorem in algebraic geometry. But what he was saying is that you're supposed to check that something is non-zero, and that can be very hard, because if something is not zero, then there's very many numbers that it can be, and it could be any of them, if all you're trying to prove is that it's not zero. Yeah, so proving the sum is not zero is very difficult. So what you can try is you can just have a computer compute values of the sum for small values of k. And when you do that, you get this sequence, minus 1, 1, minus 2, 5, minus 14, 42, and so on. I'm sure some of you recognize this. I was shocked when I saw this. These are the Catalan numbers up to signs. So the Catalan numbers have this explicit formula, but they're also these natural numbers that show up all over the place in enumerative combinatorics. Yeah, for some reason, when you compute the sum, it turns out to just be the Catalan numbers with alternating signs. And the Catalan numbers are all non-zero. So in order to prove that the sum is non-zero, it suffices to actually just prove this fact, that it is equal to these Catalan numbers with alternating signs. And yeah, so proving that it's non-zero is hard, but proving that it's equal to this specific thing, which is itself not zero, is doable. This is also not easy. So just proving this lemma takes up like 3 pages of computation in our paper. I mean, I think anyone in this audience, if I locked you in a room and told you had to do this, you'd be able to figure it out. It's basically induction and generally just known recurrences about both binomial coefficients and Catalan numbers. It's kind of a pain, but it's not that bad. And I won't say anything more about the proof, but hopefully you believe me that proving some explicit identity for a sum like this is doable, in contrast to proving that it's not zero, which seems actually rather difficult to prove without proving this. So are there any questions about this?
So you didn't manage to find any explicit, like again, no, computation-free interpretation for the left-hand side so that it is the same as the right-hand side?
No, yeah, so I don't know. I sort of suspect there must be something. I mean, there are a bunch of known identities relating the Catalan numbers to, I mean, binomial coefficients. There's also basically like partitions of k minus 1 here, I mean, ordered partitions. And there's also known relationships between Catalan numbers and partitions. And you can find in the literature simpler things that look kind of similar to this. I wasn't able to find this specific identity anywhere in the literature, and we also weren't able to find sort of purely combinatorial interpretation of this. I suspect it must be possible. There's something a little weird. The reason that it seems hard is that this is an alternating sum, so you're not just counting things, because there's cancellation, and so you're counting things but then removing some other things, and so I don't really know how to interpret this, but it's possible there's some like inclusion-exclusion type interpretation of this left-hand side, counting something related to the Catalan numbers or something. But I don't know what that would be. I'd be very interested if someone could do this. But yeah, I think the only way I know how to do this does involve a fair amount of just explicit computations with these recurrences.
Okay.
Okay, so that's the end of the proof, but because it's a complicated proof, I have a proof summary slide here where I'll show you everything that we did, and I'm going to show you it in the reverse order of what we did, so that I mean, the reverse order is also the order of the logical implications. So what did we do? So the first thing is that this complicated sum on the previous slide is non-zero because it equals these Catalan numbers. What was the point of proving that that's non-zero? That sum arose naturally as some coefficient of some polynomial in some basis. So that tells you that there is this explicit polynomial R, I mean, sort of explicit polynomial R, whose homogeneous part, hk of R, has a non-zero coefficient of this basis element in the space wk. And together with induction on k, this shows surjectivity onto all the basis elements of this wk. So we conclude that this hk is surjective onto this wk. The wk is in the image of hk. And then I didn't show you this computation, but it's true that this wk has the same dimension as the domain vk. And because we proved surjectivity between two spaces of the same dimension, this function must actually also be injective. So we find that this function hk is injective. Now, recall that vk was defined as the space of reduced polynomials that vanish to multiplicity at least k outside the origin on the hypercube. And because this function hk, which was the homogeneous part, is injective on this space, we find that every non-zero polynomial in vk must have degree actually equal to n plus 2k minus 3. So we've proved our result for reduced polynomials, that they have degree at least n plus 2k minus 3, in fact, equal to n plus 2k minus 3. And then we combine this again with steps 1 and 2 of the proofs. So step 1 was this reduction, that any polynomial yields a reduced polynomial. And step 2 was this fact that any function, if I give you the values of a function and all its derivatives up to some order on the hypercube, that has a unique representation as a reduced polynomial. So combining this fact about reduced polynomials with step 1 and 2, we're able to conclude the thing we wanted to prove, which is that every polynomial that vanishes to multiplicity at least k outside the origin while not vanishing at the origin must have degree at least n plus 2k minus 3. And so, yeah, that's everything we wanted to prove. So I have some concluding remarks, but before that, are there any questions about the proof or anything else I've said so far? Okay, great. So yeah, I just have a couple of concluding remarks that I want to mention. So the first question concerns other fields. So again, here are the questions that I started with. So there's this geometric question of the minimum number of hyperplanes needed to cover every point of the hypercube at least k times while not covering the origin. And there's the corresponding algebraic question of a polynomial that vanishes to multiplicity at least k while not vanishing at the origin. And both of these questions make sense over any field. So if I replace R by F here for any field, these questions make sense. So you could ask this question, what about this geometric covering question and this algebraic, like polynomial covering question over arbitrary fields? And you might expect that the answer should be sort of the same. So for instance, the Alon-Füredi theorem, where k equals 1, that works over any field, and the proof actually works exactly the same way over any field. And so the answer is always n, no matter what field you're working over. But actually, for this higher multiplicity question, the answer does depend on the field. So here's one thing that follows from our results. So for this algebraic question, one thing we can prove is that if you have a field and if its characteristic doesn't divide this corresponding Catalan number, then the answer to this question is still n plus 2k minus 3. And you have to be a little bit more careful, but basically the same proof I showed you works, where the point is that the final step was we had some complicated sum that we wanted to be not zero. It was equal to some Catalan number. So if that Catalan number is non-zero in this field, then basically the whole proof just works more or less exactly the same way. And so say over fields of characteristic 0, it's always the same thing. And over fields of positive characteristic, if the characteristic doesn't divide this Catalan number, then the same thing works. However, this is sort of almost an if and only if. So there's an almost converse, which is that if k is the smallest number, such that the characteristic actually does divide this Catalan number, then the answer is strictly smaller than n plus 2k minus 4. And basically, the point is that the proof I showed you is almost like every step pretty much is an if and only if. And so in particular, if this Catalan number actually is 0 in this field, then you can basically use the exact same proof to actually write down a polynomial that vanishes the multiplicity at least k while not vanishing the origin, whose degree is strictly smaller. And so, I mean, you can really do this. So here's an example. When k equals 4, and let's say over f2, over any field of characteristic 2, just by applying this reduction algorithm, you can write down this complicated polynomial that I've written here. And if you want some pain, you can check manually that this thing indeed does vanish to multiplicity at least 4 at every point of the hypercube over f2, despite not vanishing at the origin. And you can check that its degree is, n plus 4, so n plus 2k minus 4. And you can, this works in greater generality. We got this by just applying this reduction algorithm. And so you can do this. It's kind of a pain to do it, but you can do this. So again, the theorem is that if the characteristic of the field doesn't divide the Catalan number, then the answer is the same as the characteristic 0 case. I would expect that the converse is true. Our proof seems to not quite give the converse. It only works to show the converse when k is the minimal number, such that this Catalan number actually is divisible by the characteristic of the field. The reason this minimality comes in is that there was this induction on k step, and that induction on k step breaks if you've already failed at some lower k. But I still expect that this should really be an if and only if, but I don't quite know how to prove it. So that's what's going on with the algebraic question, where the answer can change over fields of positive characteristic, and the answer can depend on k in this weird divisibility way of the Catalan number. And what about the hyperplane question? So there was a recent paper by Bishnoi Boyajiska, Das and Mesarosh that came out just a couple of months ago, where they study actually a number of questions of this sort of hyperplane covering questions over f2. And so I've just written one of their theorems here. But what they're able to show is that for this question of covering every point at least k times while not covering the origin at all, the answer is somewhere in this interval. The thing to notice is that this is of the form n plus a constant times k times log n. Both the lower and the upper bound are of that form. And so this is rather different from the case of the real numbers, because in the real numbers, we know that the right answer is n plus something depending on k. We don't know exactly what this thing depending on k is, but we know that it should be n plus something depending on k. And over f2, that's really not what's going on. You really need this additional logarithmic term. And the way they proved this is actually rather nice. They showed that this question is equivalent to a basic question in coding theory, which is the rate distance trade-off for linear codes. And so basically, if you know what this means, this lower bound is basically the Hamming bound, this upper bound is basically the Gilbert-Rashamov bound. And this question is really equivalent to this question in coding theory. And they also prove various other nice theorems of various variants of this question, which I won't say much about. The upshot that I want you to have from this slide is that first, finite fields or fields of positive characteristic can be different from R. In both the geometric and the algebraic setting, there's a difference. And additionally, the geometry is also different from the algebra in this setting, where like over F2, we sort of mostly resolve this question, and they get a really different answer for the geometric question. And so something subtle is going on over fields of positive characteristic, and it suggests that there's some subtlety to this question. Okay, so to wrap up, I just want to leave you with a couple of open problems. So the first open problem is this conjecture of Clifton and Huang that I started with. The conjecture, again, is that if I want to cover every vertex of the hypercube to multiplicity at least k while not covering the origin, then I need at least n plus k choose 2 hyperplanes. And yeah, so my first open problem is to prove this conjecture, or to disprove it maybe. I think it's probably true, but I don't know. This seems hard, and the reason it seems hard is that, as I mentioned, all lower bounds really seem to rely on these algebraic techniques, and we show that at least the algebraic techniques that exist seem to have a natural barrier at n plus 2k minus 3. They can't get up to n plus k choose 2, at least without further ideas. So it seems to me that in order to prove this conjecture, you need to develop some new ideas. So I think one interesting first step would be to find a non-algebraic proof for the Alon-Füredi theorem, just that n hyperplanes are needed for multiplicity 1. If you could find a proof of this theorem that avoids algebra, that might put you well on the way to proving this conjecture of Clifton and Huang. But I don't know how. As I said, it seems that algebra is really the right tool for this, and no one knows a non-algebraic proof, as far as I know. And then the other approach you could imagine, which is what Anurag had mentioned earlier, is you could try to prove variants or strengthenings of these existing algebraic techniques, like the combinatorial Nullstellensatz, under strengthened assumptions about the polynomial, such as that it's completely reducible, that it splits into linear factors. Maybe you could prove versions of these algebraic techniques under these strengthened assumptions, and that would allow you to prove this theorem. I think either of these would be very interesting. And then the other open question, just related to what I said on the last slide, is to understand what's going on over finite fields better. We have some partial results, and this Das Mesros paper has some other results over F2, but there's definitely a lot of interesting questions remaining over finite fields. And so two concrete questions are, I mentioned this thing that if the characteristic of the field, this should be does not divide, I'm sorry. If the characteristic of the field does not divide this Catalan number, the answer is n plus 2k minus 3. I expect the converse to be true, but we can't quite prove it. I think that would be an interesting question if you could prove it. And then also the other thing I want to mention is that over finite fields, it seems that some combinatorial techniques, unlike non-algebraic techniques, seem to be more fruitful. So this Das Mesros paper really doesn't use any algebra at all. It just uses combinatorial techniques. So something's related to these codes, and something's just related to basically just induction on the dimension. And it seems that over finite fields, combinatorial techniques are actually more useful than they appear to be over the real numbers. And so this might also be an interesting place to try out combinatorial techniques in the hopes of maybe eventually, say, proving this conjecture. Yeah, and that's everything I have prepared. So yeah, thank you for your attention.
Thanks a lot, Yuval, for your great talk.
Oh. Yeah, I see Anurag saying, yeah, that's right. It seems that with what they're doing, somehow F2 really seems amenable to these combinatorial techniques, but everything they're doing doesn't seem to work even over like F3, I think. And so that's another good place to ask some of these questions.
Okay, so any other questions, comments about what Yuval have talked?
So yeah, just a comment. Over the larger fields, in general over finite fields, these things have been studied for a long time. So with the notion of this so-called multiple blocking sets.
Right.
And but yeah, there's not really that much known. That's the sad thing. Like, when the polynomial bounds are sharp, when they're not sharp for larger fields. But yeah, it's a mess. Over F2 we could do something, but in general it's very hard, it seems.
So what is this multiple blocking set?
So it's the dual problem that you have a set of points which block every hyperplane at least t times. And you are in the projective setting. So then when you apply duality, you just get the hyperplane covering problem. So this dual problem has been sort of a natural thing in finite geometry. And in fact, the Alon-Füredi theorem, for example, over FQ was already approved by Brouwer-Schreiber and Jamison in 1970s. The same thing, because they were motivated by the blocking set problem. And Ball-Serra also looked at that. They were looking at this finite field problems, which was their motivation as well.
And the previous techniques were like
the same polynomial method, yeah. So Brouwer-Schreiber is the same reduced polynomial method. It's the same, almost the same proof as Alon-Füredi. So it's not really different. Yeah.
Okay.
But there also you're not really covering a hypercube. You're really covering the whole grid, right?
Yeah, the whole grid. Oh yeah. Oh, that's
Yeah.
true. Sorry, I should say that there you're just talking about the whole FQ. Oh yeah.
Yeah.
I don't think the hypercube inside FQ, I don't think that has been studied. Yeah,
right.
That's true.
Definitely over finite fields, that's the more natural question. Where over R, that doesn't really make sense. You can't cover every point of Rn except for But yeah, over FQ, it really seems like the natural question is covering every point except for the origin.
Yeah, that's the one which has been studied, but not the hypercube inside. Yeah, that's hard. That I haven't seen at all.
Yeah.
Great. More comments or questions? Well, if not, then thanks a lot, Yuval. It was very interesting. I personally liked it a lot.
Thank you.
And yeah, so hope to see many of you next weekend.